Oh, uh, this is the second part, actually third part of sulfuric acid. So let's start with sulfuric acid's physical properties and its chemical properties, etc. There's only two properties. Anyways, let's begin with its physical properties. I have a few more books to refer to. I got a few more books to refer to for this chapter. It's Together with Chemistry, whatever the book's name. It doesn't really matter. It's just for like uh, some more reference. Anyways, so the first physical properties of H2SO4. Let's start. So the first property is its color. Its first physical property, it is colorless. Then its odor. It is odorless. It's colorless, odorless. Then taste. I know it's an acid, so people won't usually consume acids, but it has a slight sour taste. I don't know who tasted it, but it has a slight sour taste. I mean, of course, it's an acid, so of course, I think you've all had a lemon or an orange or something. They all have acids inside them, natural acids. They're very weak, so they don't really hurt you, but of course, they're sour. So, naturally we understand that H2SO4 will also be sour. Then its nature. So it's dense, oily, hygroscopic liquid. Hygroscopic liquid. What does hygroscopic liquid mean? It means that it removes moisture. I remember in the contact process when we use a concentrated H2SO4 to dry in the drying tower? Yeah, that's why it's used, because it's a hygroscopic liquid. Yeah, that's it. So the color, colorless, odorless taste, slightly sour taste. Nature, it's dense, oily, and hygroscopic. Then we have a physiological nature. What do you mean by that? Physiological nature. Physiological nature, you mean that concentrated acid is highly corrosive in nature and it chars the skin black. Concentrated acid is highly corrosive. That's it. So it's dense, oily, hygroscopic, and it's highly corrosive. Then we have density. Its regular density is 1.85 grams per cc, or you can also write heavier than water. Heavier than water. After that, after density comes the solubility. Is it soluble in water? It is very soluble in water. Soluble in water in all proportions. Then we have, after solubility, we have, boiling. Boiling mixture, a constant boiling mixture. It forms a constant boiling mixture, boiling at 338 degrees Celsius. A constant, I'll just write BM, okay? Finds a constant boiling mixture at 338 degrees Celsius. Containing 98.5% acid. There we go. Then we have the boiling point I'll just write as BP. Boiling point equal BP. Okay. 338 degrees Celsius. Yeah, that's it. And finally, its conductivity. Is it a good conductor? Yeah, it's a good conductor of electricity. So when it's a pure acid, it's almost a non-conductor, and when it's diluted, it's a good conductor. So that's why we use it in hydrolysis only when it's diluted. Non-conductor of electricity. There you go. And when it's a diluted acid, it's a good conductor. It's a good conductor of electricity. Yeah. So this is its physical properties. Let's move on. Let's just leave it there. Now, dilution of the concentrated acid is done only by addition of acetate. Okay. So, basically, what if a question comes to you in an exam? How is acid diluted? How is acid diluted? So first, for dilution of concentrated sulfuric acid, and not only concentrated sulfuric acid, in all acids, the acid is added to the water, and not the water to the acid, even though the heat is involved in both cases. In both cases, it's an exothermic reaction. But if water is added to the acid, there's a sudden increase in temperature, and the acid, being in bulk, tends to spurt out. So, when water is added to acid, there is a sudden increase in temperature, causing the acid, being in bulk, to spurt out. That's why we add oil, even in you know, even in like hot oils, we add the hot oil to the water, not the water to the hot oil. Yeah, the same reason. And what the hell is that? When acid is added to water, the reaction, the acid being heavier, acid being heavier settles down. Acid being heavier settles down. Acid being heavier settles down, and the heat evolved dissipates. It dissipates, and the water spurting out is decreased. Yeah. So when water is added to an acid, there's a sudden increase in the temperature, and when the acid is added to the water, the acid being heavier settles down, and the heat evolved dissipates, and the water spurting out is minimalized. Now there's one more thing. Distillation or boiling cannot be used to concentrate sulfuric acid. It's beyond a certain concentration. What does this mean? Okay, what if they ask you a question? Why can't distillation or boiling why can't distillation or boiling be used in concentrating H2SO4? Why not? True mystery, why not? So basically, when an aqueous solution of sulfuric acid forms a constant boiling mixture at 338 degrees Celsius, containing 98.5% of the acid, the constant boiling mixture is one which boils without change in composition. Hence, on boiling, the above mixture uh, evolves out the vapors of both acids and water in the same proportion as the liquid in the mixture. So that's why distillation can't really be used, distillation or boiling, because okay, let me write down the whole meaning. An aqueous solution of H2SO4 forms a boiling mixture of 338 degrees Celsius, containing 98.5% acid. So you can just write, as an aqueous solution of H2SO4 forms a boiling mixture of 338 degrees Celsius containing 98.5% acid, distillation or boiling cannot be used to concentrate sulfuric acid, as a constant boiling mixture is one which boils without changing composition. Hence, on boiling, the above mixture evolves out the vapors of both acid and water in the same proportion as in the liquid mixture. A constant Bm is one which boils without change in composition. On boiling, both vapors of the acid and water in the same proportion are expelled out, as in the liquid mixture. Okay, that's all you got to write for this. An aqueous solution of H2SO4 forms a boiling mixture of 338 degrees Celsius containing a 98.5% acid. A constant boiling mixture is one which boils without change in composition. On boiling, both vapors of the acid and water in the same proportion are expelled out as in the liquid mixture. Yeah. So these are all the physical properties of H2SO4. Yeah. These both are the physical properties. These are both the physical properties. Physical properties. Now let's go with chemical. there. Now let's go on with the chemical properties. Okay, for the chemical properties, I'm going to refer to the book. Okay. It's pretty much the same. I don't think we need to really refer it. Okay, chemical properties of sulfuric acid. It's acidic in nature. What does that mean? What does that mean? So, sulfuric acid acts as an acid when dilute. So, acidic nature, basically. Dilute sulfuric acid behaves as an acid when dilute. Acidic properties of sulfuric acid are due to the presence of hydronium ions formed when H2SO4 dissociates in an aqueous solution. So, the first is acidic nature. The acidic nature. So, dilute sulfuric acid acts as an acid when dilute. It's an acid when dilute. So, acidic properties of sulfuric acid are due to the presence of hydronium ions formed when H2SO4 dissociates in aqueous solutions. So, presence of hydronium ions. Hydronium ions. That's it. So acidic properties of H2SO4 are due to the presence of H3O plus hydronium ions formed when H2SO4 dissociates in the presence of an aqueous solution. Okay, there we go. So dilute H2SO4 acts as an acid when diluted. So because the acidic properties of H2SO4 are due to the presence of hydronium ions formed when H2SO4 dissociates in the presence of an aqueous solution. So the reaction goes something like this. H2SO4 is a reversible reaction. It's a reversible reaction with 2H plus SO4 2 minus. So this is an aqueous solution. Sorry, this is not the aqueous solution. Sorry. H plus. Okay, wait. Hydrogen plus water gives hydronium. So acidic properties of H2SO4 reduce the presence of hydrogen ions formed when H2SO4 dissociates in the presence of an aqueous solution. So the actual aqueous solution, the actual aqueous solutions goes like this. Okay. So H2SO4 plus 2H2O. It's a reversible reaction with 2H3O plus SO4 2 minus. Yeah. So H plus ions hydrated in aqueous solutions turn to H3O plus ions. So dilute sulfuric acid. Oh yeah. What happens when oxygen, sulfur dioxide burns in the air? It burns with a pale blue flame. Remember that. So dilute sulfuric acid turns blue litmus paper red and methyl orange pink. Okay, keep that because it's pretty important. Dilute H2SO4 turns blue litmus red and methyl orange pink. That's it. That's the dilutes. That's the dilute sulfuric acid. What about the? Okay, wait 1 second. Okay, let's talk about a few. This is all. This is all about acidic nature. After that, we'll talk about how it's a dibasic acid, then a non-volatile acid, and also as an oxidizing agent. And also as a dehydrating agent. Okay. Let's talk about the general. Reactions of dilute acid. Dilute acid. So general reactions. Of dilute H2SO4. So basically, the typical properties that the typical reactions of dilute acids. So when an active metal, an active metal in the activity series, except platinum, that plus the acid, the dilute acid, turns to salt plus hydrogen. So active metal plus acid gives salt plus hydrogen. Then base, oxide or hydroxide, plus acid. That plus acid gives us salt plus water, because it's this is known as the neutralization reaction. Then we have our carbonate, also bicarbonate. So when a carbonate or bicarbonate acts with an acid, what happens is that it forms a salt plus water plus carbon dioxide. Salt plus water plus carbon dioxide. So basically now, from if you know this, you can make any reaction. You don't have to study anything. You just have to know what it is. If it's a carbonate or a bicarbonate. If it's a bicarbonate, it'll have H. If it's a carbonate, it will not have H. I'll show you. I'll show you a few examples from the book, the other book. The other book has really nice examples. Okay. Carbonate, bicarbonate. Then what else? What else? Sulfite, and bisulfite. Sulfite. Bisulfite. This plus the acid gives salt plus water plus sulfur dioxide. Salt, water, sulfur dioxide. And finally, a sulfide. Say the difference between sulfite and sulfide. Sulfide plus acid gives us salt plus hydrogen sulfide. Hydrogen sulfide. Okay, that's it. Yeah. All you gotta know is if how active the metal base carbonate, bicarbonate, sulfide, bisulfide, or sulfide is. How much more active that is than the hydrogen. If it's more active, it'll displace it. If it's less active, I'll show you what happens if it's less active. I think in most cases, 99% cases, it'll be more, because hydrogen's pretty low. Okay, let's take a few examples. Let's take a few examples here. I'll take an example from the other book. It's a little better with examples. Here. So the acidic property, then we'll talk about the action with bases, then with metallic carbonates, bicarbonates, metal sulfides, metal sulfites, and that's it, yeah. Okay, let's first talk about the acidic property. The acidic property, what does that mean? What does the acidic property mean? I'll show you. There. Where is its acidic property? It's fine. I think it's okay. Yeah, we can skip this. I'll use this for reaction with bases and stuff. Actually, let's just start with that. Let's start with active metals, okay? Let's take a few examples. But just remember this. If it's an active metal, except platinum, plus acid, it's salt plus hydrogen, base, oxide or hydroxide, plus acid, gives us salt plus water. Then when it's a carbonate or bicarbonate, it's salt plus water plus carbon dioxide. With a sulfite or bisulfite, it's a salt plus hydrogen plus sulfur dioxide. And with a sulfide with an acid, it's salt plus hydrogen sulfide. Okay. Let's start. Let's start with active metals. Let's take an example of active metal. Let's zoom in a little bit. Yeah. So there we go. Okay, so zinc. Let's take zinc. Zinc plus H2SO4 Diluted. These are all diluted. Remember that. If it's not diluted, it won't work. This gives zinc sulfide. This happens because it's more, you know, reactive than hydrogen. It displaces the hydrogen, turns into zinc sulfide, plus what? H2. Yeah, so that's one example. Let's take two more, I guess. Or we can just take, yeah, let's just take two more. Let's take magnesium plus H2SO4, giving us MgSO4 plus H2. Then we have, let's take iron plus H2SO4, gives us Fe2SO4, FeSO4, sorry, FeSO4 plus H2. That's the example of, these are the examples of active metals, except lab. Then we have bases. Let's take a few bases example. Yeah. Bases. Okay. Let's take. Well, what do you want to take? Like potassium hydroxide, sodium hydroxide, sodium oxide. What do you want to take? So there's two types of them. I told you, oxides and hydroxides. We'll take both. So we'll start with hydroxides first. So hydroxide examples. These are the bases examples. Hydroxide, we have, let's take potassium hydroxide. Okay, we'll do balancing later. Let's first do the main thing. Potassium hydroxide plus H2SO4. What should that give? I'll displace this. So what'll be? K2SO4, because K is 1, SO4 is -2. So K2SO4 plus H2. Clearly it's not balanced. Oh, sorry, it's base, right? So it'll be H2O. So just to balance it, we do this. Pretty simple. Let's take another hydroxide. Let's take sodium hydroxide. H2SO4. Usually with bases, it'll be the base, this Na2SO4. It'll be like this, plus H2. So to balance it, we just put 2 here and 2 here. Yeah. Let's take another example, or is it enough? Let's take another example. Let's take zinc hydroxide. Let's take two more examples. Zinc hydroxide. Zinc hydroxide plus H2SO4 gives us zinc Zn2SO4. No, zinc is 2, right? Yeah, zinc's 2. So ZnSO4 plus H2O. No, it's balanced. Yeah. This is the reaction, and then we find, let's do copper. Copper hydroxide. Copper hydroxide plus H2SO4 gives us copper sulfate plus H2O. So whenever you see the 2 outside here, this won't need any balancing, and this would be just 1. I think you know how to balance equations and how to write equations. I don't need to tell you this. Now let's go on with oxides. Let's take sodium oxide plus H2SO4. This should give sodium. This should give Na2O, so it displaces this and it becomes Na2SO4 plus H2O. Same as this. What else should we take? Let's take MgO. MgSO4 H2O. The reactions are pretty similar, but not the same. What else do we have? What else do we have? Zinc oxide, I guess. H2SO4 gives us ZnSO4 plus H2O. Now let's take copper oxide. Copper oxide plus H2SO4 gives us copper sulfate plus H2O. Pretty damn simple. Okay, we're done with bases. Let's continue with carbonates. Let's continue with carbonates. Continue with carbonates. Okay. All right, great. So let's start with. I think there's only two carbonates here in the scope of Na2CO3. Na2CO3 plus H2SO4. Okay, wait. How do you differentiate? I'm gonna erase this later. How are you gonna differentiate between oxide and hydroxide? So oxide has O and this has OH. That's it. It's the only difference. So that's how you differentiate between when it's a basic oxide and a basic hydroxide. Yeah. Carbonate. Okay. Na2CO3 plus H2SO4 gives us. What does this give us? This gives us Na2SO4 plus H2O plus CO2. Because it's a carbonate, so it'll be it'll be the salt plus the water, the salt plus water plus carbon dioxide. So get an example. Let's take CuCO3. H2SO4 gives us CuSO4 plus H2O plus CO2. Is it balanced? It is. It is. It is. Yes, it is. Okay. Great. All right. Any other carbonates we can take? Can't think of any. All right, let's go to bicarbonates. When it's a bicarbonate, it's the same thing. It's the same thing. It's a salt plus water plus carbon dioxide. So in bicarbonates, let's take calcium hydroxide. Calcium hydroxide. Ooh, wait, sorry. Calcium hydroxide plus H2SO4 gives us. What's the salt? Will be the salts. K2SO4 plus H2O plus CO2. Yeah, great. So this is the reaction. So two key. Yeah. So how do you differentiate between? Carbonate and bicarbonate? So carbonate will be CO3. Bicarbonate will be HCO3. That's all. Great. So, any other reactions we can think of? See, this is sodium bicarbonate, just for the fun of it. Sodium bicarbonate plus H2SO4 gives us sodium sulfate, 2H2O, 2CO2. I think it's balanced. Yep, it's balanced. To be a precipitate. All of these are precipitates. By the way, all of these are precipitates. Except the water, of course. The water is not precipitate, but the hydrogen would be precipitate. Anyway, so that's carbonates and bicarbonates. Let's move on to sulfides and bisulfides. Sulfite. Bisulfite, and sulfide. I'll tell you the difference. Whenever you bi, you just think of H added to whatever sulfite is. Whatever it is. So let's take a sulfite example. Let's take potassium sulfite. Potassium sulfite. Yes, potassium sulfite plus H2O, H2SO4, sorry, gives us K2SO4 plus H2O plus SO2. Yeah. As a reaction, see if it's balanced. It is! And of course, SO2 would be a precipitate. I'm not going to write that in every reaction, just always as precipitates. Let's take another example. Let's take Na2SO3. H2SO4 giving us Na2SO4 H2O SO2. It's balanced, yes. So that's for sulfide. And now for sulfite. Bisulfite. Again, this is nothing but as you can see, sulfite is SO3. This would just be HSO3. So I'm not gonna write the difference down again. NaHSO3 plus H2SO4 giving us Na2SO4 H2O SO2. Yeah, there. It's balanced. Yeah, it's balanced. Great. Let's take another example. Let's take another example of potassium. Potassium bisulfate. Potassium bisulfate plus H2SO4 plus H2SO4 giving us K2SO4 plus 2H2O plus 2SO2. Yeah. So for any bisulfate you can do this. And sulfite. Now let's go with the sulfide. The sulfide. Sulfide. What is a sulfide? It's only S, by the way. Whenever you think of sulfide, it's only S. Okay, sulfide. So again, sulfide is only S, bisulfite is HSO3, sulfite is SO3. Okay, after this page we will stop. Wow, this takes way too much time. Anyways, Na2S plus H2SO4. What is for this? It'll be hydrogen sulfide. So Na2SO4 plus 2H2, no, there's no water in this, just H2S. That's it, right? Yeah, this is a double displacement reaction. These two exchange their balances. Anyways, let's take another one. ZnS, H2SO4, ZnSO4, H2S. So another one, FeS, H2SO4, giving us FeSO4, H2. Oh, sorry, H2S. It's actually iron 2 sulfide in the new IUPAC system, but whatever. Yes, so this is still 2 more pages left. Wow, this is taking some time. Okay. Let's move on. But in the next video. So here we've learned a lot about reactions. Wow, look at that. Look at how many reactions we did just in this video. This much. We did this much in today's video. We covered a lot more syllabus than last time. Oh wait, this much. Wow, that's a lot. We covered that much, and this also was covered in the same time. But this is more conceptual. This is more, theoretical. And theory is not that hard on this. Alright, thanks for watching. Bye.